Smackmaster C here, looking at chapter 13 of the engineering. I'm going to go through the entire chapter really quickly, okay? We first opened up with the story in Genesis 11, 1 through 9, the story of the Tower of Babel. Look it up. There's definitely some engineering stuff here, some civil engineering action going on. They do believe the tower was a ziggurat. And the ziggurat about 3000 BC looked like this, but this is the artist's idea of what the Tower of Babel may have looked like. Happened in the southern Mesopotamia, modern day Iraq. Okay? 4. Now, why? What's up with civil engineering? Well, you're building safe facilities to meet societal needs. Like what? Public works projects, roads, bridges, dams, municipal water systems. Okay, what else? Well, there's different subfields within civil engineering, so you can look at structural engineering, water, okay, resources, water resources, transportation, environmental, construction, and geomatics engineering. This is more related to geomatics engineering here. Okay, geomatics, you're looking at measuring, analyzing, and using spatial, that means 3D space, data from many sources like satellites. There's different purposes for the satellites. Some it'll be land, airspace, water areas, in some cases possible construction sites or areas where there are mineral deposits. Professional aspects, pretty much it's straightforward. You need at least a bachelor's degree. If you're an engineering technician, an associate's degree works. There is the American Civil Society of Civil Engineers, also International Association for Bridge and Structural Engineers, Institute of Transportation Engineers, and the American Planning Association. Civil engineering principles do cover quite a bit of knowledge. They have to understand structures. Well, what do we mean? Arranging the parts that they would remain stable while being able to withstand forces, like structural loads, when you're putting something heavy, for example, on a bridge. That would be good, okay? There's also structural forces that are involved. Those would be forces that the structure itself puts out. Structural components, structural materials, structural analysis, okay? So when we look at loads, we're looking at how structures transmit the load from the structure into the ground. Static loads are non-moving, dynamic loads are moving. So when we talk about equilibrium, okay, we have opposing external forces and they transfer the load throughout the structure. So here's an example here of two diagrams that shows equilibrium. 50 newtons up, 50 newtons down. They're opposite forces, therefore they cancel each other out. So the box isn't going to move up and down, right? It's static. It's going to stay there. 30 newtons to the left, 30 newtons to the right. That is also stable, and nothing is going to change for that. We looked at structural forces in terms of bridge, okay? Where you have compression and tension forces. Where you have a load, it could be a box, it could be traffic. You have compression where it's pushing down, but you also have tension which is pulling up, especially in terms of the cables. Now there's movement, like there's shear movement, there's bending, and there's torsion. Torsion, think twisting. So beams, like structural components, like a floor joist, like you're seeing here in this picture, a column, okay? Then you have braces, like struts. Making sure that an engine is secure, although I've seen more struts dealing with car batteries to keep them secure in the engine compartment. Ties like this that will allow pieces of wood to be nailed in securely, and then joints which will unify two pieces there. So it makes it one on the surface, not necessarily underneath here. We looked at the idea of tension tie and compression strut. So when you look at these, they're both the same shape. It's a right triangle. One is right side up, the other is upside down. So this is a tension, and the tension is here. Okay? Whereas when you're looking at the load's being pushed on this, but it's also being supported by this. This is a compression strut, for example. When we look at structural materials, there's all kinds of things. Every material has abilities and disabilities, so to speak. It's depending on the property of the material. Structural analysis. Well, that goes into the area of structural engineering. You got to make sure that the structure has sufficient strength to hold up the loads. You ensure that the structure is efficient as possible. In other words, it doesn't cost too much. You use the minimum amount of materials needed to get the job done and properly. You make best use of the materials. So you still need to throw in physics, especially mechanics where you're dealing with statics and dynamics. Okay? Then we talked about civil engineering software. Now, that gets to be field specific if you're dealing with designing a bridge, for example, or you're designing a skyscraper, for example. All those things come into play, and they also include symbols in there. Trusses. These are examples of a structural component known as a truss. A truss is a triangle, okay? And you can see there, those are trusses used in the real world. Now, the simplest truss is triangular. The structural members are pinned together and are called joints. The truss analysis, you start with the free body diagram, you determine the structural stability of it, calculate the reactions and the internal forces. Now, complex calculations can be done by computer software. So, here's a free body diagram, a basic truss system, where you have structural members and joints. The circles that you see here are, in fact, the joints where parts of the truss come together and they join, and they're bonded together. The individual lines that you're seeing there, those are called members. So there is actually a formula that can be used to calculate if the truss is stable or not. So here's an example of an unstable truss. This is the formula here. J stands for joints, M stands for members. So 2 times the joints that you have should equal to the number of members plus 3. So when you look at this unstable truss here, you have 1, 2, 3, 4, 5, 6, 7, 8 joints. So 2 times 8 is 16. In theory, if this thing is stable, it should also have 16 members. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, wait. So plus 3 is 14. 16 is greater than 14. This is an unstable truss. But if you go and add another member here and another member here, that changes it from 11 to 13. 13 plus 3 is 16, which is equal to 16, and therefore this is your stable truss. This one is not. Okay? So that's one way to calculate it. Now, with a free body diagram, you can also put in what are the forces that are involved in there. And again, that does incorporate physics. Civil engineering applications like bridges, skyscrapers, geomatics engineering. We looked at bridges, talked about things like the length of the span, what kind of a foundation are you going to have, what are your available materials, that would be a big deal, and basic parts like piers, abutments, and roadway. Okay, so again, bridge components, this is just giving you an example of what's there as part of the bridge. This is typical bridge elements. Beam bridges span short distances. This is a truss bridge here, which typically you see that for like railroads, but you can use those for regular cars. This is a beam bridge, okay, and this is in Florida. This is a cantilever bridge where you have an upward structure and a downward structure as well. That's called a cantilever bridge. Now, we also have the arch bridges. Now, arch bridges rely on the arch strength. The strength is the capstone. The capstone is what keeps the arch intact. The Romans used it for aqueducts, but we've also used it for bridges. Not just for freeways, but for railways as well. You're distributing the load to the abutments. The arch can support the deck from above or below. Depends. Suspension bridges, again, it's It's very similar to an arch bridge, except it's kind of inverted. You use tension forces like cables. The main parts, you have towers, main cables, and anchorages. So think like San Francisco's Golden Gate Bridge. That's a suspension bridge. Specialty bridges are like combination bridges, where you can combine two building techniques into a bridge, and then you have a movable bridge. That picture there is an example of a movable bridge, because the bridge can be raised. Okay? Skyscrapers. Okay, structural frame is our skeleton. It withstands the building dead load. Okay, so in other words, if you build a building, it should be able to withstand that. You attach it to footings, and piers extend deep into the earth. This supports the structure, and it gives extra support. The outer surfaces doesn't carry the weight. You do have a central core inside the skyscraper where it helps resist the wind. It's more resistant to earthquakes, and it contains elevator shafts and mechanical systems. So lots of skyscrapers are built with these in mind. So if you look at a skyscraper built in Chicago, resisting the wind would be a good thing because Chicago's a windy city. If you're building a skyscraper in Los Angeles, you want more resistance to earthquakes. So that's where you have your trade-offs. Okay? So this is a diagram of the different parts. So you have the core in the center there, and then you have all these beams that are there. You have your ground level, and this is under the ground level here. Okay, you have your joists going across there supporting the floor. This is your frame, and then you have your curtain wall. Okay? And that can be made from different things. All right. How about dams, tunnels, and geomatics engineering? These are other structural civil engineering applications. Like that dam right there. Here's a clue. If you look at the whiteness of the rocks, that tells you where the water level has been in the past. Just saying. Okay. Geomatics engineering, you're looking at where are the locations of objects on the earth. You create land and resource maps. You can conduct boundary and other land surveys. You design. You use the GIS. That's the satellite system for that. That helps. Okay, land surveying. That would be kind of important. What land belongs to whom? Measurements used to determine the size and the shape and the piece of the land. You measure the distance and the angles. Oh my gosh, we're using trigonometry in the real world? Yeah, actually. Total station instrument includes the electronic distance meter, the EDM. So it's not electric dance motion or electronic dance music. Total robotic station. Moving on. Surveying bearings. So what does that look like for surveying? The bearings are expressing the line direction. So what's the compass direction that the line is going in, and how many degrees are you dealing with? Okay, so that's where you get quadrant systems and the angles that are found measuring it from the north-south axis. So, for example here, you got south 80 degrees, west 100 feet. Okay? As we're winding down here, ladies and gentlemen, civil engineers work in teams. And that's where the ethics comes in. Okay? You have the U.S. Army Corps of Engineers. There is military works, government projects, civil works projects, and they have also been used in combat. And with that, ladies and gentlemen, I'm going to stop here. And that's it, folks. Toodles.